and welcome to Computer Science. This is the third episode about the Arithmetic and Logic Unit. And it's called the ALU for short. So, we're looking at something that's basically an XOR gate, like we saw in the last episode. But this time, we're still using the NAND, but in the middle of it, we're bringing out a carry. So there are actually two outputs, a carry and a sum. And the carry is always A and B. So this is the half adder. It can add one bit to another bit. And the bits are called A and B. Then we can add 3 bits, A, B, and C. So we add A and B, and we get a carry and a sum. And then we add C to the sum of the first half adder. So I guess this is C plus A XOR B. And then that also gives out a carry and a sum. The sum is just going to be the sum of the whole full adder, but the carry is going to be ORed by another carry, by the other carry from the first half adder. And that's how you add 3 bits. But this is how you actually add 2 8-bit numbers. So one of them is called A and one of them is called B. They start at AU0 and B0, and you keep putting full adders. There are 8 full adders. And all of the sums are these F's. F0, F1. Yeah, those are the sums. Eventually you get to a carry out. And that's actually when you overflow all of those over 8 bits, and you actually have to go to the 9th bit. Sometimes in Pac-Man this is a problem, because when you get to level 256, well, the last level was 255, so level 256 will be totally messed up. And I think you remember that from that first episode, we showed this thing called 2's complement. It turns out that first place is -8th place. The second place is the 4th place. The third place is the 2's place, and the 4th place is the 1's place. So it makes sense. -8 plus 4 plus 2 plus 1. Well, 4 plus 2 plus 1 is 7, and 7 minus 8 is -1. So that's why -1 is 1, 1, 1, 1. And here's how you convert no's complement to 2's complement. So the symbol we're going to use is a box with a 2 on it. So we're going to invert all of the bits in the input, and that's, by the way, is called 1's complement. But it has a problem where it's always off by 1. So we add it by 1, and yeah, that's the second 8-bit number, 0, 0, 0, 0, 0, 0, 0, 1. And if you have a carry out there, well, it just goes to ground. You don't need that. And all of the sums go down to the output. And this is how you convert 2's complement back to no complement. This is the shape of a box with a 0 on it. So this time you add everything with a bunch of 1s. Again, the carry out will go to ground, and everything, and that would be 1's complement, but you have to convert it back to no complement. So by nodding everything, it goes back to no complement. So to subtract, and the sign for that is a box with a minus on it. So we're going to use the actual names of this. So the one that you're subtracting from, which is the one on the top, it's called the I don't know what it's called. I think it's called a subtractor, maybe. But the second one, the one on the bottom, is called the subtractor. The one you're subtracting by. So you know that so we have to add those, and then but the answer is still in 2's complement, so you have to convert it back to no complement. So we use that 0 thing. So then we have this thing called a comparator. It may seem familiar to you because that's the exact thing we saw in the last episode when we were trying to vote for president. So it has a positive and negative, and this is basically the greater than. You can see that the right part of a comparator symbol is a greater than symbol, and yeah, I just noticed that myself. So it takes a positive and a minus, and so take the positive and a negative, and it subtracts the negative from the positive. All of those differences goes away, and only the sign has to remain. Well, problem solved. It seems like this time now the 3 people beat the 1 person, and they vote true, or yes, vote for the serious guy. Bye. See you next time.